Right, let's now go on to this is lecture 24 and 25. So before we go into the stuff about the residue theorem, I just want to speak about singularities and classifying them. Classifying singularities. In other words, what types of singularities are there? Some are removable, some are essential. So let me just give a short resume of what they are about. Then we'll work our way towards the celebrated residue theorem. So you recall the Laurent series. I can write a function f of z in the shape of some bk over z minus z naught to the power k, from k equals to 1 to n, plus some ak z minus z naught to the power k, from k equals to naught to infinity. That's a Laurent series expansion. The new thing, if you look at this here, this is the Taylor series. Part here is the Taylor series. You can always expand about the point z naught with the shape. And this coefficient here will be the k derivative divided by k factorial. The addition now is this guy here. Now you've got something below the division line. So now you have negative exponents. That's the new thing here. Negative exponents. So k is 1, like f of z minus z naught to the minus. K is 2, z minus z naught to the minus 2, and so on. So you now have a series of positive terms and negative terms. A new thing compared to what we've done in the past. So now focus on this n. If n is finite, then we say we have a pole of order n at z equals to z naught. Like for example, if you have a function f of z, let's take it something over z minus 4 cubed plus something over z minus 4 squared plus something over z minus 4 plus, there'll be nothing with z minus 4 now, plus something z minus 4 to the 1 plus something z minus 4 squared, and so on and so on. So it starts off with a couple of negative terms. The highest negative term is what we call the pole. So we say it has a pole of order 3 at z equals to 4. So we look at the highest negative term. Highest negative exponent. We say it has a pole of order 3 at z equals to 4. What we can do, we can expand f in a punctured disk. Now you should know what we're talking about. So the point z equals to 4 is removed, but it doesn't mean that all is lost. You can still draw a circle around that point and do an expansion of f of z in the disk. A complex function can have an expansion in a disk, even if it's not holomorphic at z equals to 4. Another example I can take, just make an example up. F of z equals to, say, z squared plus 2z minus 8 or z minus 3. Before we say that it has a pole of order 1 at z equals to 3, we must make sure that things can't cancel off and stuff. Because if the z minus 3 cancels off, it's not a pole. So the way to check is to do the long division. Z minus 3 goes into z squared plus 2z minus 8, unless you can factorize it. But if it's not a quadratic, if it's some long polynomial, you wouldn't know. Z goes as z times z squared minus 3z subtract, that's 5z minus 8, z plus 5, 5z minus 15, so 15 minus 87. So we can say here the answer is z plus 5 plus 7 over z minus 3. So now it's clear that z minus 3 is a pole of order 1. So there's a pole of order 1 at z equals 3. This is just words now, right? But pole means the highest exponent, highest negative exponent. I'll try to follow this example here, which is a bit of a tricky one that's in the book. That's why I thought I'll explain it. So it's example number 40. Prove that f of z equals to 1 over 1 minus cos z as a double pole. This means second order pole at z equals to 0. It means that if you expand the function, there should be a 1 over z squared that appears by itself in the expansion. That's what it means. If this actually works, it's going to appear a 1 over z squared when you do the expansion. Okay, so let's try to expand this. Now you can always expand anything, guys. Anything, any freaky function I make up, sin z over cos of e to the ln sine hyperbolic z. Find an expansion of it. You can. Because as long as you can differentiate it an infinite number of times, and you can differentiate anything really, then you just do nth derivative over n factorial. That will give you the coefficients. So you can do it for anything. Even if it's a series, you can write it as a, if it's a series 1 over something, that will happen here. You can convert it to a series with a positive exponent. So, proof. So let's take this f, which is 1 over 1 minus cos z. So you may know that cos z is 1 minus x squared or z squared. 1 minus z squared over 2 factorial is even, right? Z squared over 2 factorial plus z to the 4th over 4 factorial minus z to the 6th over 6 factorial, and so on and so on. That's the expansion of cos z. Now, if you do 1 minus 1 at the bottom, you end up getting 1 over z squared over 2 factorial minus z to the 4th over 4 factorial plus z to the 6th over 6 factorial minus blah, 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 blah. Then I pull out the z squared from the bottom, z squared into 1 over 2 factorial minus z squared over 4 factorial plus z to the 4th over 6 factorial, etc., etc. Okay. Now, since f is even, the denominator is also even, and the part in brackets will be expandable as something a plus bz squared plus cz to the 4th plus dz to the 6th plus blah, 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 blah. So I'm saying that this part here, this yellow part, is 1 over, right? You can't invert these, of course. You can't say that 1 over this is 1 over 2 factorial minus 4 factorial over z squared. That's rubbish. You can't do that. So you got to find a way. Can you write this as a power series like that? The answer is yes. I said, as long as you can differentiate something infinitely, you can always put it in the shape of a Gaussian. And I have also argued that the terms will all be even numbers because this is even. Cos is even. In any case, how do you know something is even? If you replace z by minus z, it stays the same. It's reflexive about a change of z to minus z, or reflexive about the y-axis, remember. I can't really speak about y-axis now because a complex function z is made up of two things, x and y. There's two parts, or u plus iv, you could say. But naively, if you replace z by minus z, it remains the same. Cos minus z is cos z. So it's even. That's why I can argue that it will be a plus bz squared plus z to the fourth, etc. You won't find cubic terms and fifth powers and stuff like that. That's what I'm ruling out. So to conclude, f of z will be 1 over z squared into this stuff here. It doesn't actually matter what the a, b, c, and so on are. It doesn't matter. It's something, some number. You can find the coefficients using the Taylor series coefficient stuff. So this will give us something over z squared plus b plus c z squared plus d z to the fourth plus blah, 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 blah. Clearly, f has a pole of order 2 at z equals to 0. Where is this pole? Well, here's here. A over z squared. Oh man, come on, this is so slow. That's the pole of order 2. A over z squared. The other stuff are all positive exponents. The highest negative exponent is 1 over z squared. That proves that the function f of z has a pole of order 2. In other words, it's not always transparent and obvious. You won't always get a 1 over z minus 3 squared. You may have to do some work before you actually get it out. Any questions? Anything that's not clear to you? This is expansion of cos z. It won't work for sine z because sine z is odd. And in any case, with sine z, the expansion of sine z is z minus z cubed over 3 factorial plus z to the 5 over 5 factorial. You won't get the 1 minus 1 cancelling off like you did here. We profited from the fact that over here, 1 minus 1 cancels off. If you have a sine function there, then the game is different. All right, now let me talk about the word essential singularity. Just mention it briefly. The essential singularity. This is when the negative exponents are infinite. The n is infinite. For example, if you take e to the 1 over z minus 1, I expand e to the z. It's 1 plus z squared over 2 z over 1 factorial plus z squared over 2 factorial plus z cube over 3 factorial, blah, 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 blah. But now the exponent is not just z, it's 1 over z minus 1. So it will be 1 plus 1 over z minus 1 plus 1 over z minus 1 squared over 2 factorial plus 1 over z minus 1 cubed over 3 factorial and so on and so on. In other words, 1 plus z minus 1 to the minus 1 plus 1 over 2 factorial z minus 1 minus 2 plus 1 over 3 factorial z minus 1 to the power minus 3 and so on. So it doesn't terminate, doesn't stop. So we can say there's essential singularity at z equals 1. I mean, you can build this for anything, even if you want cos of 1 over z minus 1. You will have a 1 over z minus 1 appearing everywhere. You can't remove it. So the negative exponents are just going to carry on. And it's 3 minus 4 minus 5 minus 6 up to infinity. It's not like it stops somewhere, like we had in the previous example. So for our purposes, that's not a useful series. It's boring. We want the one where it stops. That will give us the Laurent series expansion at the residue theorem, which is now where we are going to go to. The residue theorem. So let me just give you the fluffy, the woolly bits here. Say F is analytic in a punctured disk R, centered at a singular point Z naught. Now, f of z has a Laurent series expansion here, which we have written before as f of z equals to sum of ak z minus z naught to the power k, from k equals to naught to infinity, plus some bk over z minus z naught to the k, from k equals to 1 up to some number n. Oh, now here I'm going to just define something, and then I'll show you how it links up with the work at hand. This exponent here, you see, those are all the negative terms. In the BK department, you've got AK and BK. AK part is all positive terms, Taylor series. If you add the negative term, you call it Laurent series. Huh? On the negative department here, when K is 1, then it's something over Z minus Z naught. That's a special item in this entire analysis. So we make a definition here. We're just giving it a name. Definition. The coefficient of B1, the coefficient B1 rather, the coefficient of, let's say, Z minus Z naught to the power minus 1 is B1, is called the residue of F at Z naught. Written residue of F of Z at Z equals to Z naught. That's how you write it. I'm just calling that the term with K equals 1, this BK, B1, called the residue. Just give me a name. I mean, you can call it anything. So I haven't done any mathematics yet, I've just given you a name. Now you'll see it has a special characterization. So by the Laurent series theorem, which we've done in the last lecture, the BK had a specific value 1 over 2 pi I f of w, w minus z naught k minus 1 dw. The dk was given by that formula. That was the coefficient for the negative exponent by the Laurent series theorem. That's from the last lecture. And if you specialize to B1, put k equals 1. It's 1 over 2 pi I along a contour C1, f of w, so 1 minus 1, 0. Anything to the power of 0 is 1. So it becomes harmless, like this. In other words, the first coefficient, the coefficient of the 1 over z term, or 1 over z minus z naught, if you like, is simply the integral of f of w. That's the crux of the matter. The integral, well, if I just reverse this, or I can say the integral of f of w dw. I can even change it to z, guys. Along a certain contour is 2 pi I b1, or 2 pi I, the residue of f of z at z equals to some z naught. That's the residue theorem. This coefficient b1 has a spectacular appearance now in the game as killing this exponent. The k equals 1 is no w minus z naught. We're just left with the integral of f of w dw, or f of z dz. W is a w variable. So then, I can say the integral on a closed curve C1 of f of w dw is 2 pi I b1, or 2 pi I, the residue of f of z. Z equals z naught. What is the meaning of residue? It's a coefficient in the Laurent expansion of the term of 1 over z. You know the number in front of 1 over z. That's the answer to the integral test. The integral, you don't have to integrate. That's the beauty. If you know that you can expand something in the Laurent series, you just read off the coefficient of 1 over z. Then gives you the answer for the integral. There's no need to do any high-bound integration techniques from first year like Hebrew methods integration like part. These techniques. Here, integral is simply the coefficient. That's numbers. Integral is just a coefficient. Of course, you know in mathematics it's never as easy as that. Sounds easy. Somebody can make it easy to think. The thing is that how do you write the Laurent series and how do you pick it out? You need some experience in that. So now I'm going to take a few examples, show you how it works. Oh, okay. Let me just crystallize the theorem for many singular points. See, I dealt with just one point there. Residue theorem, multiple poles or multiple singularities. Suppose again F is analytic on and inside a closed contour C. Except at some bad points, Z equals to say Z1, Z2, Z3, and so on. Suppose there's a couple of bad guys in the game. In other words, it's singular at these points. It's like dividing by Z minus something. Z minus 3, Z minus 10, Z minus I. Those are bad points. Suppose you have a couple of those bad guys in the game. In other words, so you have like a closed contour like that. C. Well, let me call the closed contour. Let me just call this a domain D. So we have a few bad boys. I said Z1, Z2, Z3, Z4. You can have many. Now we have a closed contour around that called C. C. We know the positive sense of the rotation is that. Direction is important. Okay, so let me write down this thing here, rule. Positive sense is counterclockwise. Also, if we walk on a contour, the region is always on our left. This is a convention. So if you walk on a contour, so let's say you're walking here, here you are. You're walking, what? If you're walking in that direction, if you look on the left, you see the region. The region is this part here, inside. The inside of it, on your left. Now, to prove this theorem, what we need is to surround each of these bad points by a circle. We surround each of these bad points by a circle, singular points. I'm assuming there's 4 of them. So now the region is inside there. These are the points that make up the region. I call the region. Remember, if you're walking on a contour, the region must always be on your left. So now, suppose you were standing here. Which way must you walk? Because the region is on your left. Suppose you are here. If you walk this way, okay, I'm facing this way here. I'm walking down this way here. Can you see on my left is this side here? But then the singularity, the circle, it's not the so-called region. The region is that side. That's the wrong way to walk. I should walk this way. If I walk this way, now the region is on my left. The region, anyway, I stand here, outside, the region is on the outside. So, the moral of the tale is the sense of rotation now is this way. For all of these guys. No, that one is wrong. This way here. In other words, it's clockwise for the circles. Circles are now clockwise, but the region C is counterclockwise. So there's like a minus into the picture here. So we can call this contour C1, C2, C3, C4. Okay, so maybe you may find this a bit, I explained it as a rule, but I can also explain this by using those tubules, if you remember earlier on in the game. Remember some time ago I said, draw a thin thing that's connecting, draw a thin tube that connects the two, so you make one nice big region. In other words, put tubes here, walk down there, stop here, walk inside. You cannot work like this. It becomes opposite. Like, look, you're walking there, somewhere the tube will walk down here. Then you carry on walking in the normal place. Come to this place, walk inside. Again, you're walking opposite. In other words, clockwise. Come back down to tube, come back and carry on like this. Then I said the integral over those tubules, one is going in, one is going out. They kill each other. The integrals cancel off. So it's useless. Or you can say make the tubules infinitesimally thin. They cancel off in any case. But it explains why the notation is different. There's two ways I've explained it. Any questions on that? Something you may not find believable. All right, then I can enunciate the theorem like this. If you are believing all of that, then I can say the contour integral of f of z along C will be the residue at each of the points, but you add them up. So there's 4 points. You find each residue here. So it's like 2 pi I. So each f of z. No, hang on, I should write this as residue of f of z. Residue of f of z at every zk. So where k goes from 1 up to some number n. In this case, n is 4. That's the residue theorem. I mean, that's the residue theorem. The proof is easy. I said enclose each zk by a small circle ck. Then the contour integral along c of f of z minus sum of all these integrals here, f of z dz from k equals to 1 to n along each ck will be 0. Why is it 0? Because this guy is going one direction, those guys are going counter, going opposite. If they were all going in the same direction, then you have a plus here, and the answer should still be 0, because that's the Cauchy-Gaussian theorem. I will have excluded all these bad boys here, and I'll have a nice continuous. See the orange dots? Make a nice continuous region with no similarity. No, I simply walk around here, walk in this tubule, go around this guy, come back, go around here, go this side, go around here, like that. And if you look at the orange part, there's no singularities inside the orange part. Singularities are surrounded and removed. So the Cauchy goes at here and tells me, if there's no singularity, the integral is 0. The integral, contour integral, in a totally holomorphic region, or totally analytic region, is 0. So that's what I'm using here. The only reason there's a minus here is because of, yes, what? The opposite directions. This guy goes counterclockwise, these guys are going clockwise. So the minus direction. This implies that the integral of f of z dz from c, or c rather than c1, c is simply 2 pi I, the sum of the residue at each point, f of z at z equals to z k, and k equals to 1 up to n. So find the residue at each point, add them up, and we are done. The big question is, how do you find the residue? How do you find the residue? Remember, what is the residue? Residue is the coefficient of 1 over z. Or residue is the thing that you find in front of 1 over z minus 2 or something, to the power 1. The first negative term, in other words, the first negative one gives you the residue. The coefficient is the residue. You want me to pause for 5 minutes? Let me pause for 5 minutes while you take that in, stretch your legs a bit, and then after the break, I will